So our Roman 2 now, we're going to see bend or V shape. So bend or V shape. So let's take a typical example of one of water. Water would droop. So the molecule of water, you see, that's why I told you that the linear compound is AB2. But B should not have, or A should not have load of electron. But we saw an exception in the case of CO. So that's the only exception. Then let's see this case. In this case, we are going to draw the Lewis representation of water to actually see what's happening. The Lewis representation of water will have O. O is bonded to H, also bonded to H. You have two lone pairs of electrons on water. The two lone pairs of electrons will repel the bonded pair of electrons. They will repel it on one side of the plane, thereby giving water a V shape with a bond angle of 104.5 degrees. It's not just water that has a V shape. We can have the one of hydrogen sulfide. So hydrogen sulfide also. Hydrogen sulfides. So here we can have sulfur, bonded to H, lone pairs of electrons. So the lone pair of electron also pushes these H atoms on one side of the plane, thereby giving a covalent bond, a V-shaped structure. So here the bond angle is 104.5 degrees. So the next type of shape we're going to see a trigonal planar. Because there are two types of trigonal. There are trigonal planars and trigonal pyramidal. We're going to see trigonal planar. Trigonal planar. Trigonal planar. Roman 3. Trigonal planar. For trigonal planar, the molecule should be of the form AB3, such that A does not have a lone pair. A should not have a lone pair of electrons. Example, a typical example, we can take the molecule of BF3. So boron trifluoride. So let's draw the dot and cross diagram for boron first. So we have boron trifluoride, which gives boron plus 3 molecules of fluorine. So the boron atom, the configuration for boron is here we'll have 5, 2:3, fluorine 9, 2:7. So let's draw the dot and cross diagram. Having boron, 3 electrons in the outermost shell. So each of the boron electron will combine with one of the fluorine. Here we're having like that. Fluorine. Exit. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So if you want to draw the Lewis representation, we're going to have on this. Boron F. So the molecule of boron, or the compound boron trifluoride, is trigonal planar. What does it mean of tri? Tri means 3. So I have 3 fluorine atom bonded to 1 boron atom. So at the end of the day, we have a trigonal planar shape because the boron atom has no lone pairs of electrons. That is why the three fluorine atoms spread itself on the plane equally. So they will repel themselves equally, thereby giving a trigonal planar shape. So the bond angle here is 120 degrees. So what is the difference between trigonal planar and trigonal pyramidal? So let's now see an example of trigonal pyramidal. Trigonal pyramidal. So in the trigonal pyramidal, we are going to have, let's take the case of ammonia. Ammonia that we have been drawing ever since. So here's ammonia. We saw that ammonia was having a lone pair of electrons from the structure that we drew. There were a lone pair of electrons on the nitrogen atom. So let's put that lone pair of electrons here. 1, 2. H. We see that BF3, NH3, they have the same morphology, such that they form AB3. But what's the difference between trigonal planar and trigonal pyramidal? For trigonal planar, the central atom has no lone pairs of electrons. That is why we have a planar structure. Then, for a pyramidal structure, we have that the central atom has lone pairs of electrons. So this lone pair of electrons pushes the bonded pair of electrons on one side of the plane, thereby giving the structure a trigonal pyramidal structure. So that is just like a pyramid. That's why we say trigonal pyramidal. So it's nitrogen that is at the summit. Then the hydrogen atoms are like that. Just because of the lone pair of electrons. So the lone pair of electron that pushes the bonded pair of electron on one side of the plane. The bond angle is 107 degrees. So these bond angles are determined via X-ray spectroscopy. So the bond angle are experimental angles or experimental values. We have now the next shape we are going to see is trigonal bipyramidal. Trigonal bipyramidal. 1, 4. Trigonal bipyramidal. Such that we have AB5. A typical example is phosphorus pentachloride, so PCl5. So with all the Lewis representation, we have PCl5 like this, Cl, 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 Cl. So we have Cl, PCl5. So that's the molecule of PCl5. We can have our last molecule, 1, 5, octahedral. So they form AB6. We can have a sulfur hexafluoride. Have the molecule of sulfur hexafluoride. Yes, sulfur. Fluorine. So that is sulfur hexafluoride. So that was all about lesson 3. Lesson 4 means we're going to see intermolecular forces. Lesson 4. Intermolecular forces. The intermolecular forces we are going to start with A. Van der Waals forces. An intermolecular force is stronger than a chemical bond, sorry, is stronger than an intermolecular force. Then the intermolecular forces act between molecules, or the interaction between molecules, and the action actually influence the physical property of a compound, like the melting point, the boiling point. So those are the two main factors that are being influenced, or the density, the viscosity. So these intermolecular forces actually act on the physical property. The chemical bond actually act on the chemical properties. So the first intermolecular force we're going to see is van der Waals forces. So the van der Waals force is a weak intermolecular forces that act due to the interaction between the molecules of mostly covalent compounds. So the covalent compounds are actually, there's an interaction. It's a weak intermolecular forces. Then what is the effect of these van der Waals forces on molecule? Let's take the case of halogens. Halogens. Fluorine, chlorine, bromine, iodine, astatine. Gas, liquid, solid. As I'm moving down the group, the physical state changes from gas to liquid and to solid. This is due to an increase in the strength of the van der Waals forces. So, what actually leads to a variation in this physical state is the van der Waals force. But the van der Waals force increase as the molar mass increase. So the smaller, the larger the molar mass, the stronger the van der Waals force, and the molecule will automatically have a solid physical state. Like the case of iodine and astatine, the molar mass is larger. That is why they are solid at room temperature. If you take the cases of fluorine and chlorine, both of them, they are gases at room temperature because they contain weak van der Waals forces. So the van der Waals force actually influences the physical states of a compound. And also, the compound should be a covalent compound. So the van der Waals force in gases is weaker compared to liquids, compared to solids. So our next type of intermolecular force we are going to see is dipole-dipole attraction. Dipole-dipole attraction. B. Dipole-dipole attraction. In the dipole-dipole attraction, here in this case, we're going to see that the attraction is done between a less electronegative element and a more electronegative element. So let's take the case of hydrogen fluoride. So hydrogen fluoride. Hydrogen, or moving across the period, electronegativity increase. The halogens are the most electronegative element. Across the period, electronegativity increases. So fluorine is more electronegative than hydrogen. So fluorine will drag the electron cloud towards itself. So I have fluorine drags the electron cloud towards itself. At the end of the day, fluorine becomes sigma minus, while hydrogen becomes sigma plus. These sigma plus and sigma minus are temporal, or that temporal, they're partial, sorry, I can say partial positive and negative charge. There is an intermolecular force, or there is an electrostatic force, is electrostatic in nature, holding the sigma minus fluorine and the sigma positive hydrogen. So in this case, they will have a partial positive and negative charge. So in this case, we're having a dipole-dipole because we have two poles. One pole is positively charged, the other pole is negatively charged. In this case, we have dipole-dipole attraction. The dipole-dipole attraction is also found in aldehydes and ketones. If you have an aldehyde molecule like this, RC, double bond OH, sigma minus, sigma plus. In this case, it's an aldo compound. Sigma minus because oxygen is more electronegative than carbon. We can have a keto compound. RC double bond O, R, sigma minus, sigma plus. But what you have to note here is that a dipole-dipole attraction are stronger than van der Waals forces. This explains why the boiling point of, let's say, propanal is higher than that of propane. So the boiling point of propanal, which is an aldehyde, is higher than that of propane. Propane, which is an alkene. This is because dipole-dipole attraction are stronger than van der Waals forces. So our next, we are going to see hydrogen bondings, which will be our last intermolecular force. Hydrogen bondings. Hydrogen bondings. See, hydrogen bondings. So a hydrogen bond is formed when hydrogen is covalently bonded to one of the three most electronegative elements. The electronegative element here will have fun. Fun means fluid, oxygen, or nitrogen. Once hydrogen is bonded to fun, the resultant bond will be a hydrogen bond. And hydrogen bond is not a bond, but is an intermolecular force. The hydrogen bond is stronger than dipole-dipole attraction or van der Waals forces. It's one of the strongest intermolecular force on the periodic table. Example of elements or compounds, with a hydrogen bond includes, we can have the molecule of hydrogen fluoride, ammonia, water, alcohols, carboxylic acids, of hydrogen fluoride, water, ammonia, water, alcohols, carboxylic acids. Then let's now see how these hydrogen bondings have influenced the physical property of compounds. Let's take the case of the hydrogen halide. The hydrogen halide here means HX, where X is halogen. We have example hydrogen fluoride, like we stated up here, hydrogen chloride, hydrogen bromide, and hydrogen iodide. So in this case now we have the various of hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide. So let's see how hydrogen bonds influence the boiling point of this element. In this case, we are going to plot a graph of boiling points of elements against the gram or the molar mass. So let's plot the graph. So you have a graph of boiling point against the molar mass. From our graph, we observe that hydrogen fluoride, hydrogen bromide, hydrogen chloride, hydrogen bromide, hydrogen iodide. So we clearly see that, okay, hydrogen fluoride have an exceptionally high melting and boiling point. This is simply because hydrogen fluoride contain hydrogen bondings. Hydrogen bondings are stronger than van der Waals forces. This explains why hydrogen fluoride have an exceptionally high boiling point. The other hydrogen halides, they have van der Waals forces, but the van der Waals force increase as you move down the group. That is why the hydrogen, the melting and boiling point increases from hydrogen chloride to hydrogen iodide. Even though the van der Waals forces are weak, but as you're moving as you're moving down the group, the strength of the hydrogen of the van der Waals forces keep on increasing. That is why we're moving from hydrogen chloride to hydrogen iodide. The van der Waals forces increase. There's an increase in the boiling point of the compound. The hydrogen fluoride, due to the fact that it has hydrogen bonds, have an exceptionally high melting boiling point. Also, this influence also is at the level of water. We clearly see that water boils at the temperature of 100 degrees Celsius because water has 2 hydrogen bodies. So here, like a bonus, we're going to see the difference between a chemical bond and an intermolecular force. So differences between a chemical bond and an intermolecular force. Differences between a chemical bond and an intermolecular force. Intermolecular force. 1. A chemical bond is stronger than an intermolecular force. 2. A chemical bond acts between atoms or ions. An intermolecular force acts between molecules. The next, a chemical bond influences the chemical property of a compound, while an intermolecular force influences the physical properties such as density, viscosity, the melting, and the boiling point. There was a similarity between the two. Both involve electrons interaction. Both lead to the formation of stable compounds. So we arrive at the end of our lesson of today, of our chapter of today. Our chapter of today was actually chemical bondings and intermolecular forces under the matter and transformation, that is still module 1. And we saw the introduction to chemical bond, and we define a chemical bond as any electrostatic force of attraction that exists between atom or ions in a given substance. Went forward to see lesson 2, that was type of chemical bondings. We saw an ionic bond, a covalent bond that was divided into 2. We had a simple covalent bond and a dative covalent bond. Went forward to see a chemical bond. After chemical bond, we saw the shape of molecules. Under shape of molecule, we saw a linear, trigonal planar, trigonal pyramidal, trigonal bipyramidal, and octahedral shape. Then we went forward to see at the intermolecular forces. Under the intermolecular forces, so the van der Waals forces, which is the weakest electrostatic force of attraction. We have after van der Waals for when dipole-dipole attraction. After dipole-dipole attraction, we went forward to see hydrogen bondings, which is obviously the strongest intermolecular forces. We ended our class of today with the differences between a chemical bond and intermolecular force. It's still Mr. Coblin, your chemistry teacher. Follow more on Educlynk. Thank you for watching.